Hi folks. So today we're going to talk about springs. Springs are generally considered in our class just a coil, generally of metal, with some quantifiable stiffness that's pretty constant to the spring. But springs don't necessarily have to have all the same stiffnesses. That's going to be a property of our spring. Springs are really useful. They're very useful for modeling elastic materials. And we say elastic here as a term to describe materials that have a restoring force in them when you deform them. So for a spring, for example, if I start to pull it, right, there's a restorative force to restore, to go back to our normal shape. And if I push on it, again, restorative force to actually expand back out. So I want to start off by, again, just saying that we usually think of springs as some sort of coiled metal. A coiled metal here is our, it's going to be our spring here, and we're going to label that this spring has some equilibrium length, right? Equilibrium length. This is just our normal length of the spring when there are no net forces working on it. When there are no net forces working on the spring, I have an equilibrium length. A lot of times I'll write L0, but sometimes we can label it something else. So restoring forces, so that equilibrium, by the by, just a little spring here, right? Our equilibrium length is important because any distance past that equilibrium length, right, and I'm going to experience a restorative force, a spring force. So we're actually going to use Hooke's law. Let me introduce Hooke's law as this force. So Hooke's law says that there is a force equal to negative k delta x for a spring that is being compressed or stretched. So let's break this down. Obviously I have some sort of force. This is our spring force. I have this delta x. Delta x here is the distance past equilibrium, right? I'm going to say, actually it's displacement from equilibrium. So if I have an equilibrium length of, let's say, I don't know, about an inch here, a little bit less, yeah, a little bit less than an inch, right? And I start to displace it, right, to some amount here, maybe a centimeter, half an inch, right? Now I have some sort of force working on it. But that displacement is only going to be half an inch-ish, right? Then I also have this K. K ends up being our spring constant. Earlier in this video I talked about the springiness, the stiffness of a spring being inherent to the spring, being a quantity, a characteristic of the spring. That is K. K quantifies how springy this spring is, right? The bigger K is, the harder it is to actually compress and to pull out. The softer a spring is, right, the easier it is. Think of like a slinky or something like that. It's going to have a much lower K value. And then there's this negative. What the heck is that guy doing? The negative is the restorative nature. Restorative? I'm bad at spelling, guys. That doesn't look right. Well, we're going with it. It's the restorative nature of this force. If I have a negative displacement, meaning I'm pushing on this spring, right, then the force is going to be positive. It's going to push back out. it's going to be negative of my negative displacement. Another way of saying that, if I pull on it, right, then the negative is going to say, I want a force in. So this actually quantifies the restorative nature of this force. This is Hooke's law. So springs impose this linearly increasing force per displacement. And this is for ideal springs, of course. Ideal springs. When we're talking about ideal springs, we're saying that they are massless. Again, is that a good assumption? We could do worse. We could do worse. If we're thinking about shocks on a car, probably not massless. If we're thinking about, a spring inside a little pen, a ballpoint pen, it's pretty massless. We're also saying that there's no internal friction. Internal friction. So it doesn't, or resistance maybe. So it doesn't take any amount of, I feel like I'm defining things using its own definition, but it takes no energy to actually compress things. It doesn't sap any energy out of the system. We're saying that anything involving a spring, the spring is part of that that system. All right, it's not part of the environment. The last thing I want to talk about is the work done by springs. All right, the work done by springs. Now, I go through a little bit of a derivation in my notes online. You can take a look at those. I'm going to kind of skip to the punchline here because I'd rather spring. I want to talk about how to use this rather than go through lengthy derivations at the moment. So the work done by a spring, if you integrate the spring force over the distance that you're working with, we actually get negative 1/2 k delta xf squared minus 1/2 k delta xi squared. Another way of writing that is, so this is some delta something or another. I would get negative delta whatever this stuff is, 1/2 k delta x squared. So this 1/2 k delta x squared is actually a potential energy. Right? And I said that chapter 10 is going to be all about potential energy and the interplay between potential energy and kinetic energy. I'm skipping a beat here. I'm actually going to talk about this a little bit early. This is the elastic potential energy. Now, potential energy, as just a really loose working definition, is again how much energy is stored in an interaction. How much energy could be turned into movement energy or kinetic energy. So it's that possibility for movement, is that possibility to start becoming more energetic. We're going to talk about this again more in chapter 10, but this is our elastic potential energy. And what we're saying is the work done by the spring is the negative change in that. Right? So that's a little preview of what's to come. So that's springs in a nutshell. If you have any questions, again, feel free to drop a question into my inbox or swing by an office hour, and I'm happy to talk about this more. Next time we're going to finish up the chapter by talking about power, and then we'll have a few example